In this section, we discuss the Legendre symbol. Let P be an odd prime, namely a prime number that is not equal to 2. From our theorem 4 above, we know that in this case, not all elements are squares. So we are interested to know what elements are squares in the field of characteristic P. Let X be a non-zero element in Fp star. The Legendre symbol of X, denoted by parentheses x over p, is the integer x to the power p minus 1 divided by 2. And it has only two values, plus minus 1, from the discussion in the previous section. From here, the Legendre symbol is defined for all the non-zero elements in Fp star. And we can naturally extend this to all of Fp by setting that 0 over P is just 0. And now we would like to further extend this definition. We want to define the Legendre symbol for all integers x, not just those in this finite field Fp. How do we extend it? Recall that any integer x has a natural image in Fp. And we denote this image by x prime. Remember, this natural map is given by z to Fp by sending an integer n to n times 1, where 1 is the multiplicative identity in the finite field Fp. So we can define for an integer x, its Legendre symbol modulo p to be the Legendre symbol of x prime mod p. From here, you can see immediately that when we extend this definition to all of the integers, then if two integers x and y are congruent modulo p, then they have the same Legendre symbol. Suppose x and y are congruent modulo p, then we can write x equal to y plus kp for some integer k. And then if we take the p minus 1 divided by 2's power, we see that this guy, if you use the binomial theorem, is congruent to y to the p minus 1 divided by 2 modulo p, because all the other terms are divisible by p in the binomial expansion. And it's also clear from the definition that the Legendre symbol is multiplicative, just by definition. And in the fancy mathematical language, this means that the Legendre symbol is a character. And now let us review our proof of the part B of our theorem 4. In this proof, we see that x to the power q minus 1 divided by 2 is equal to plus 1 if and only if y to the q minus 1 is equal to plus 1, where y is the square root of x in omega, where this omega is an algebraic closure of fq. And this happens, meaning x to the q minus 1 divided by 2 is equal to plus 1, by our proof here, if and only if that y is in fq star. And that in turn is equivalent to that x is a square in fq. And you can see immediately, this is precisely what the Legendre symbol is describing. Precisely when q is equal to p. Remember, in this theorem, q is the power of p. Now let's take q precisely equal to p. And in that situation, the Legendre symbol is x to the p minus 1 divided by 2, which is equal to y to the p minus 1. So we can summarize this in the following statements. First, the Legendre symbol of x mod p is equal to 1 if and only if x is the square mod p. And second, if x has y as a square root in an algebraic closure of fp. Then its Legendre symbol is precisely y to the power p minus 1. For the rest of this section, we shall compute the Legendre symbol of x mod p for 3 particular values for x. And to this end, we shall introduce 2 functions of integers. If n is an odd integer, we let epsilon of n and omega of n be elements of z mod 2z defined as follows. Epsilon of n, by definition, is congruent to n minus 1 divided by 2 modulo 2. And omega of n is by definition congruent to n squared minus 1 divided by 8 modulo 2. And we can make these two more explicit. This is equal to 0 if n is congruent to 1 mod 4, and is equal to 1 if n is congruent to minus 1 mod 4. And this omega n is equal to 0 if n is equal to plus minus 1 mod 8, and is equal to 1 if n is congruent to plus minus 5 mod 8. And this can be verified directly by elementary calculation. To verify this, because n is assumed to be an odd number, we just take n equal to 2k plus 1, where k is an integer. And you can see that epsilon of n is really epsilon of 2k plus 1. And by definition, this is what? This is just k mod 2. And omega n will be congruent to, and now this is 2k plus 1 squared minus 1 divided by 8. After simplification, this is k times k plus 1 divided by 2 mod 2. You know this guy is always an integer because k and k plus 1 must be divisible by 2 because one of them must be an even number. And from here you can see that if n is congruent to 1 mod 4, that means k must be an even number. And in that case, this guy will be simply equal to 0 modulo 2. And the case when n is congruent to negative 1 mod 4 happens exactly when k is an odd number. And when that happens, this guy is equal to 1 mod 2. This is slightly more complicated, but also easy to verify. The case that n is equal to plus minus 1 modulo 8 corresponds to the case when k is either a multiple of 4 or congruent to 3 modulo 4. And when this happens, this guy is an even number. So this is equal to 0. And the second scenario, when n is equal to plus minus 5 modulo 8, happens when k is equal to 1 or 2 modulo 4. And when this happens, this guy is an odd number. So it is equal to 1 mod 2. So this is the explanation for these two functions of n. We can actually view epsilon and omega as two group homomorphisms. This epsilon can be viewed as a group homomorphism from the group of units of the ring Z mod 4Z to the additive group Z mod 2Z. Remember, this is a group of units consisting of two elements, 1 and negative 1. These two elements are the only two elements that are invertible in the ring Z mod 4Z. And this home sends 1 to 0 and sends negative 1 to 1. And similarly, omega is a group homomorphism from the group of units of Z mod 8Z still to the additive group Z mod 2Z. This is a group of 4 elements, 1, negative 1, 5, negative 5. So these are the only 4 elements here in this ring that are invertible. And this group home sends plus minus 1 to 0 and plus minus 5 to 1. So this precisely corresponds to the thing going on here. Now we are ready to state our next theorem, which computes the Legendre symbol of x mod p for x equal to 1, negative 1, and 2. First, the Legendre symbol of 1 mod p is equal to 1. And second, the Legendre symbol of negative 1 mod p is -1 to the power epsilon of p. And the Legendre symbol of 2 mod p is -1 to the power omega of p, where epsilon and omega are defined as above. And now let's prove this. Number 1 is clear. Because if x is just 1, then it's p minus 1 divided by 2's power is also 1. So this is just 1. Number 2 is also easy. This is because -1 over p is -1 to the power p minus 1 divided by 2, which is by definition over epsilon p. And the number 3 is a non-trivial part. To prove it, we let alpha be a primitive 8th root of unity. In an algebraic closure omega of fp. Remember, this means alpha to the 8th power is equal to 1, but any lower power is not equal to 1. But in the algebraic closure omega, we can see immediately that alpha to the 4th power is equal to -1. This is because in the algebraic closure omega, this equation has 2 solutions, z equal to plus minus 1. And because alpha is primitive, alpha to the 4th power cannot be equal to plus 1, so it has to be -1. And therefore, from here we know that alpha to the 4th power plus 1 is equal to 0. And if we divide both sides by alpha squared, that is alpha squared plus alpha to the -2 equal to 0. So the element y, defined as alpha plus alpha inverse, satisfies the equation y squared equal to 2. This is because alpha plus alpha inverse squared is alpha squared plus 2 plus alpha -2, which is just 2. Furthermore, we have y to the p, which is alpha plus alpha inverse to the pth power by the Fleischmann's stream. This is equal to alpha to the p plus alpha to the -p in the field omega of characteristic p. And now let's see how this connects to our group home omega. If p is congruent to plus or minus 1 modulo 8, then we see that y to the power p, which is alpha to the p plus alpha to the -p, by the fact that alpha to the power 8 is equal to 1. So this congruence relation gives us this is equal to alpha plus alpha to the -1, which is equal to y. And therefore, the round symbol of 2 modulo p in this case is equal to 2 to the p minus 1 divided by 2. And remember, what is 2? 2 is equal to y squared. So let's plug in y squared here. And this is y to the p minus 1, which is 1. So this is the first case. And in the second case, if p is congruent to plus minus 5 modulo 8, then what do we have? We have y to the p is alpha to the p plus alpha to the negative p. In this case, let's reduce to alpha to 5 plus alpha to negative 5. But we can further reduce this guy, because alpha to the fourth power, remember from here, alpha to the fourth power is equal to negative 1. So this guy becomes negative alpha, where that negative 1 comes from alpha to the fourth power. And the second part becomes negative alpha to the negative 1. But what is this? This is precisely negative y. And now, it follows that the Legendre symbol of 2 mod p, which is 2 to the power p minus 1 divided by 2, which is y squared to the power p minus 1 divided by 2, which is y to the power p minus 1, is equal to negative 1 here. At this point, if you follow me carefully, you'll notice that I forgot to explain two things. I forgot to explain why y to the power p minus 1 is equal to 1, and also why here y to the power p minus 1 is equal to negative 1. To verify this guy, we need to conclude it from the equation y to the p equal to y. And we need to show that y is actually non-zero. Why is y non-zero? That is because y squared is equal to 2, which is non-zero. And this follows from the assumption that p is not equal to 2. We are not in a field with characteristic 2. So 2 is not equal to 0. So y squared is not equal to 0. And therefore, y cannot be equal to 0. So the equation y to the p equal to y will imply that y to the p minus 1 equal to 1. And same thing happens here. But in this situation, we have y to the power p equal to negative y from here. And this finishes the proof. We have shown that when p is equal to plus minus 1 mod 8, this 2 over p is 1. And when p is congruent to plus minus 5 mod 8, 2 over p is negative 1. And that precisely corresponds to the definition for omega fin. So we are done. Finally, we make a remark for our theorem 5. By the proof of our theorem 4, we know that x is the square mod p if and only if x is in here by our notation, if and only if the Legendre symbol of x mod p is equal to 1. So theorem 5 can be rephrased as follows. -1 is a square mod P if and only if P is congruent to 1 mod 4. And 2 is a square mod P, which means this omega of P is equal to 0. Happens precisely when P is congruent to plus minus 1 modulo 8. So that's a remark for theorem 5.